Jonathan, the stage is yours.
Thank you. So hello everyone, and thank you for coming here to this junior researcher webinar. So I can go straight to the to my plan. First, I will start by giving you an introduction on what are multi-nucleon transfer reactions, so MNT, and giving you some motivations to study them. Then I try to answer with you to the question how to use the MNT as a mean of production for new isotopes, before moving on to one specific experiment that we did in 2023 at Argonne National Laboratory using Xenon 136 on uranium-238. Then I'll give the preliminary results of my analysis before moving on to my conclusion and outlooks. So first with the introduction, and I start with one motivation. So here you can all recognize the single chart of nuclei. I give you for reference the heaviest known double magic nucleus, lead 208, and here on the upper right part you have the island of stability, which is the next set of theoretically predicted magic numbers with n equal to 184 and z equal to 114, 20, or 28, depending on the model. And one interesting thing talking about the quest for new super heavy nuclei toward this island of stability is that they have been all historically produced using fusion-evaporation reactions. Yet, if one wants to do such an experiment nowadays, it will face some limitations. Namely, you will have limited choices for your beam and target combinations, and if you plan to produce new elements, you will have very low cross-sections to do so. To give you an example, the organeson, the heaviest element ever discovered, was discovered with 3 nuclei in an about 3-month-long experiment. So this highlights the need to find new paths to synthesize new super heavy nuclei. And then one of these paths could be MNT reactions. Here is typically the kind of area we typically want to populate with this mechanism. This thanks to a higher N over Z ratio due to different beam and target possibilities compared to fusion, so we produce more neutron-rich nuclei, and also we have some promising theoretical cross-sections to do so, but you will see later. And so now the idea is to study the mechanism on heavy nuclei, so on actinides, and this towards the synthesis of new super heavy elements. And now, before moving on to the properties of MNT, I'd just like to show you this slide to highlight that using multi-nucleon transfer reaction isn't just about producing new super heavy elements. So this is again some single chart. This is coming from Argonne National Laboratory's website, and this is their estimated rates for the upcoming n equal to 126 factory, which is an apparatus which has the purpose to produce new isotopes for further study at this facility. And so this here, you have in red outline the known part of the chart, and all these squares give you rates for production rates at this facility. And what's interesting here is that they intend to see new isotopes ranging from almost oxygen up to the heaviest ever known. So using such a mechanism could unlock new physics cases all along the chart. And this is why we see many projects starting worldwide in many different facilities such as RIKEN, Ivascula, Leniaro, or even Ganil, and so on and so on. So now for the properties of MNT. Well, let's start by sending a beam on a given target. They will hit with some impact parameter, and if it's low enough, they will be trapped together in some potential well. And then from that, we have a first key feature of the mechanism. that they won't fuse completely into a compound nucleus. This would indeed be the fusion path. But indeed, you will have nucleon flows that are created one way and the other before they eventually separate. You end up here having your what we call the primary fragments right after the reaction, and from that we can give another feature of the mechanism, which is that we have large distributions of exit channels. To give you an idea, in some experiments, it's of the order of 10 nucleons transferred. But then you have you have an inelastic process, you have some energy dissipation, which can indeed be rather large. It's possibly of the order of hundreds of MeV, leading to neutron evaporations before gamma emission, of course, down to the ground state, but also when you're working with AV elements, you can also have some fission that happen. And all of these make your secondary fragments. Finally, one last feature is that if you look at one given exit channel, it will have also large angular distribution, angular compared to the beamline, which is of the order of few tens of degrees. So, now let's answer the question how to use MNT as a mean of production, following the properties that you know. So, if you plan an experiment, you will first want to choose a beam and a target. And to choose that, we have some theoretical predictions in the framework of the quest for two new super heavy nuclei that I'm going to show. So here are two models. The first one from Adamian et al. Describes the MNT as the evolution of a dinuclear system, and doing so they have some rather promising cross-sections up to the nanobarn. Their favorite case here is to choose some rather light beam, so namely calcium-48, because using such nuclei, you will have a strong shell effect that will increase the survival probability of your primary products, thus increasing cross-sections. And so there were some experiments to study that, and I'm going to show some done at JSI using SHIP, a velocity filter, or TASCA, a gas field separator, and in both cases, they were able to find some very massive transfer channels. For example, here we start from curium here, and they've seen all of these channels through alpha decay studies. They were even able to discover 5 new proton-rich isotopes. So we have in many different cases here a lot of massive transfer channels that have been identified, but no cross-section measurements. Then, for this second model, it was developed by Zagobayev and Greiner first, and is now extended by Karpov and Saiko. It makes use of multidimensional Langevin equation to describe the dynamics of the reaction. But here, they rather favor the use of heavier beam, much heavier. Indeed, they predict that the best are the heaviest possible. See here, uranium and curium, which is their best predicted physics case. And this is because when you do so, you will have a lot of neutrons available for transfer, thus increasing the probability to transfer some and reaching the new neutron-rich AV or super AV isotopes. Again, they have very interesting cross-sections. And so, here again, we have some experiments that tried to compare. Here, they used a xenon on a thick lead target, and they measured the total cross-section for their products. So, the target is here, and they've been able to to see and measure all these nuclei with some very massive transfer channels again. And from that, they try to compare with the algebraic model, and they've seen that they have a very good agreement with theory indeed. But so, at the end of the day, we have two different kinds of models that predict different choices for beam and target combinations, and with no proof that one model worked much better than the other. So, this one is still an open question, and we need more data to compare with the best theoretical candidates. Then you have your beam, you have your target, you want to know at which energy you will send your beam. So again, to answer this question, I have some results to show. Here is a very recent experiment from Dubna using xenon-136 and uranium-238 at 1.11 GeV. And thanks to their setup, they were able to reconstruct the mass distribution of the fissioning and non-fissioning LV partners. So let me explain. This is the mass of, here is the mass of uranium-like nuclei, and you have two different curves, 2 body, 3 body. 3 body means the xenon correlated with the surviving uranium-like MNT product, while 3 body means xenon-like plus the 2 fission partners after fission of the AV-MNT products. And one interesting thing here is when we look at the heaviest mass. Comparing both curves, you see that the survival probability of heavy fragments will quickly drop down to 0, as we have no more 2 bodies, but still many 3 bodies. And this is why, because this is explained by the fact that they were at a rather large energy, which was indeed which was helping to have products above fission barriers after reaction. So, if we are too high in energy, we lose everybody through fission. And this is well illustrated by this other experiment here. It's nickel on lead. It was an experiment at JSI where they measured cross-section distribution as a function of their beam energy. And you can clearly see this trend here through this right-tailed Gaussian shape. Looking at that, if you increase the energy, you start to lose almost all your products. Cross-section drop down to 0. So because they are either fissioning or evaporating. But then, if you want to go to the other way, you have a lower limit too, of course, because you have some interaction barrier. And if you're below this barrier, you will have, the cross-section will go down to 0 again because you will have no more nuclear interaction. So, at the end of the day, you end up having a rather narrow beam energy range where you will have a reasonable cross-section value for a given project. So for beam energy, you want to run near the interaction barrier, which is basically the Coulomb barrier, with some fine-tuning that may be necessary. And finally, you know that your experiment is ready, you have your experimental conditions, you want to ask yourself at what angle you should detect your product. What are the angular distribution? So again, let's have a look. This result is a cross-section distribution from a rather old experiment where they measured some potassium ion. And here you have on y-axis the energy of your ion, and on x-axis the angle. And indeed it's a contour plot with cross-sections value here. To explain that, let's take some scheme. So we have again our beam sent on a fixed target with a given impact parameter. If the impact parameter is too high, your nuclei are too far from each other, you will have no nuclear interaction. Nothing will happen except some Coulomb scattering. So you have nothing. And if you come closer, you have a smaller impact parameter, there will be, at some point, a specific value of this parameter, which is related to a scattering angle known as the grazing angle. This value is where nuclear interactions start to dominate over Rutherford scattering. If impact parameter is below, you have more nuclear interactions than Coulomb interactions, than pure electromagnetic interactions. And around this value, we typically have the highest cross-section considering the integrating over all the exit channels. But this is the misleading thing for many. It's the highest cross-section, but looking at anything. Because here, as you are not that close, nuclei are not that close for each other, you're in a quasi-elastic process. And so you will only transfer few nucleons. But now, if we want to produce new isotopes which are very exotic, what we want to do is to perform some central collisions. Here, we will be in a deep inelastic regime where we can see massive transfers. Because in this case, we have a very small impact parameter, so the beam interacts and then goes backward. And here is the way of having the longest interaction time and the highest overlapping of your nuclear wave functions, enabling massive transfers. So the maximum of the total is not where you want to see. You want to look at forward angle. And then let's have a look at some predictions in the framework of super heavy elements. It's again the uranium and curium case, so the favored one for the Zagreb-IF's model of using Langevin equations. This plot here shows you kinetic energies as a function of mass number. You can first recognize that we have this maximum, this quasi-elastic maximum here. You are in this part, you have a very low energy dissipation and a very, very high cross-section for transfers with outputs that are around your target mass. But then we want to go to the deep inelastic regime, which is where we have a lot of energy dissipation, so in this part. And we want to look at super heavy elements at the highest mass. So two things. First, you can see that, according to this prediction, these super heavy nuclei are not at all produced in the quasi-elastic regime. You definitely need to go here. And if you select this set of data, and you look at the angular distribution, at the end of the day, you see that they are all going at forward angle, so central collisions. Indeed, if you put a cut, you have everything if you put a cut of your angle below 20 degrees, more or less. So you definitely need to look at forward angles, and from that, we move on to the experiment that we did in 2023. So it was using xenon-136 and uranium-238. And first, I'm starting by summarizing the goals of this experiment, which was to find the optimal conditions to produce new isotopes. So we had a xenon-136 beam because it's nuclei that have high N over Z ratio. So we favor the production of neutron-rich nuclei. And also, we have very high beam intensities available as it's stable. Then the target is uranium, so we want to produce uranium-like nuclei, actinides, and we want to measure their cross-sections looking at forward angle and with a near-barrier beam energy in order to look at how the mechanism behaves at this very specific position. So now about this setup, we had this xenon beam that was produced by the Atlas Linear Accelerator and sent on a pure metallic the uranium target, which was on some rotating wheel to sustain higher intensities. Here you can see it in the target chamber. And around that, we had the high purity germanium detector array Gammasphere that was enabling the measurement of gamma and X-rays coming out of the de-excitation of the produced nuclei. But then we wanted to look at forward angle, so we had the gas field separator AGFA that way, which main purpose is to separate the scattered beam from the MNT products or uranium-like nuclei that are going towards a focal plane. Focal plane which was made up of two detectors, mainly a PPAC, which is a gaseous detector, and then a DSSD, so double-sided silicon detector, where nuclei are implanted. With that, you can perform what we call a prompt spectroscopy, correlating what's in the recoils in the focal plane to the gamma they emitted and which are detected in Gammasphere. But then we have some other detectors. We had some silicon tunnels all around the DSSD, and then behind them, some germanium Clovers, X-ray, and together we can perform a decay spectroscopy of what is implanted in the DSSD. But here, I will not talk about decay spectroscopy and focus on the prompt spectroscopy. So now, let's just talk a bit about the analysis. And here you have some scheme of the setup again. So your MNT products go through AGFA, they are bent and sent towards a focal plane. With your detector, you measure position and energy loss in flight, so with the PPAC, and then the total implantation energy in the DSSD. With these observables, you can select the recoils of interest. Then you want to look at the gammas, so you're going to correlate them, and you're going to build time of flight between your gammas and the detection of the recoil that emitted them in the PPAC. With this, you have a time of flight that you can use to select the relevant gammas. And finally, you look at your gamma spectra from Gammasphere to try to identify MNT product. So this is what it looks like. It's my recoil correlated gamma spectrum. Here you can see some very intense peak all along the spectrum, but these are indeed coming from the ground state rotational band of uranium-238. So it was the target of our experiment. It's thus coming mainly from Coulomb excitation, and it is a background. So it is a background for our experiment. We want to suppress it, and to do so, what we do is to perform some gamma correlations. So now we move on to my preliminary results, starting with this by explaining how this gamma correlation works with an example. So let's take a uranium-240 in an excited state. It's the +2 neutron transfer channel. Let's take the ground state rotational band, and as it's excited, it's here right now. What's going to happen is that it will emit gammas of known energies all the way down to the ground state within at a sub-nanosecond scale. So for detectors, this means that we detect all of these gammas almost at the same time. But so we can correlate them easily. And what we do indeed is to make triplets of energies to make all possible triplets of gamma energies and to put it in a fully symmetrized three-dimensional plot. So this is what you call a cube, and here is the result. So again, we have our ground state rotational band here for reference. This plot here is the total projection of one axis of my cube. And how we use cube? Well, what we do is to apply some gates. So we apply 2 gates on 2 axes and look at what remains on the third one. So here, let's say we want to apply a gate on this transition and this transition, trying to see some other peaks. Indeed, let's try to look at the peak in between right here. And if we look at the result. So this is this spectrum. We have this peak here that come nicely out of the background and help us identify uranium-240. So now, from this, we want to identify all the other reaction products, of course. And here is then the full list of what I've been able to identify up to now. So these stars show you uranium-238. Black dots are preliminary identifications, while black dots with red dots inside are what I've been able to confirm. So 5 uranium isotopes up to now. And from that, we now want to compute some cross-sections, of course. So here it is. This plot here give you a cross-section distribution as a function of mass number for uranium isotopes. So we have two different things here. The red histogram here is a result from theoretical calculations using the Langevin model that was given to us by Karpov and Saiko in private communication. And these 3 black dots are my measurements, my preliminary measurements for uranium-234, 6, and 40. From that, what we can say already is that, it seems to follow nicely the trend from Karpov. We can say that it is very, very good agreement with prediction. But then, this is not our only tool, because we also have access to some semi-classical simulation code that is called DIT, and that I used to simulate my experiment. So I used it together with Gemini++ for evaporation and fission, and in blue here is the result that come out of the simulation. So of course it hardly match data and is very different from Karpov's calculation, but then we have paths for this give us hints to improve DIT. Indeed, we may know from what makes this difference, and this is because DIT make the assumption that every nuclei is spherical, which is of course wrong, but when you look at the interaction at the Coulomb barrier, it will indeed depend on the fact that the nuclei is deformed. It will play a part in the interaction barrier, because then, depending on the orientation of your two nuclei, they will face a different barrier, and then you can see here that this change a lot the result as we are running very near barrier. So, to conclude, you've seen that MNT reactions are foreseen as a promising mechanism to produce neutron-rich PV nuclei, but not only, yet they are changing to study. We have done an experiment in 2023 at Argonne National Laboratory to study the MNT products from xenon on uranium at forward angles. It's under analysis, but we already have some first cross-section measurements that first are in good agreements with Karpov's and Saiko's prediction for fusion-nucleon transfers and at forward angle, but also looking at the DIT code, we have room for improvement, and indeed we have already some ideas to play with. But finally, even if the evaluation is still in progress, these results suggest that we should keep investigating the mechanism towards more exotic nuclei. Thank you for your attention.
Thank you very much, Jonathan, for this very nice talk. So now if anybody has some question to ask, please feel free to raise your hand. Yes, Valérian, you have a question?
Yes, Jonathan, thank you for this interesting talk. I remember you showed the spectra before with the results, the preliminary results that you just showed. Yes, this one. And I was wondering, because you said you already have now other elements that you have identified as preliminary. Did you reach the point where you can put them on the spectra? And if so, is there anything, or there is no more uranium isotope? Maybe this I missed. Maybe.
Well, for other elements, okay, I have hints of some other elements, but the changing thing is that, well, if for the plus or minus one proton channel, will be complicated as it's at least even old nuclei. So for gamma spectroscopy, come back to cross section from gamma spectroscopy, it will be a bit complicated. Then for plus or minus two proton channels, well, I have hints. I'm not sure it's not totally confirmed. And well, maybe if I have some luck, I can have some. I can give some values. But yet it's not done using exactly the same process that I've done for other isotopes. So it will be a bit more complicated to compute.
Okay, I understand. Thank you.
Are there other questions? Yes, François?
Yes, about this experiment. It is it was made at one energy, and then there is a spectrometer behind it, and you measure at one rigidity. And what energy? Why you choose this energy, and the rigidity also? Why you choose this rigidity? Is the optimum in the production, and also, do you accept the full production, or you have just a part of the production?
Okay, so first the energy. Indeed, we have two different beam energies for this experiment. We have some 800 MeV data, but we had a lot of experimental changes during this experiment. Just to give you an idea, the data that I show you is about 14 hours of data, and well, I have nothing much working with all of the rest of the experiment, because well, it was indeed very changing. We were pushing the boundaries of this setup. So why these energies? Basically, 700 MeV is more or less at the barrier computed in some way, slightly below, but okay, we don't know exactly where is the real barrier value. 800 MeV should have been at around 10% above, but at the end of the day, we don't understand fully how it works. So any value would have given interesting data. But so, well, I have only the 700 MeV data to work with. And then for the magnetic rigidity, it's a gas field separator. And everything becomes much more complicated when you work with a gas field separator, even more since this is not the usual kind of experiment rerun on that kind of separator. Because with this, doing interactions between AV and AV nuclei, we have products with a lot of kinetic energy that are much more than what, and much more than in fusion experiment. You have much more velocity. Sorry. So we're kind of out of the usual working range of gas field separators. So we couldn't easily predict the optimal values, and we did scans, indeed.
And the results you present are produced after a scan of rigidity, the one that when you compare to theory.
It's we tested some different values, but okay, it was even more complicated than that, because you have at 0 degree, you have also the beam that is coming into the separator. And of course, you have a lot of beam. So the beam magnetic rigidity should be, to give you values, beam magnetic rigidity was measured at 1.15 decimeter, and the uranium-like nuclei at 1.65, but yet, as we have a lot of beam, we have a lot of scattered beam along the separator. So we have the tail of the Gaussian that is still a lot in our data. And if we changed the separators setting too much on one side, well, we had too much xenon entering. But then this prevented us to have the exact optimal window for uranium-like.
Okay, thank you very much. It was a nice presentation. Thank you.
Thank you.
Alexis, you have a question?
Yes, thank you, Jonathan, for your presentation. I just have a question regarding the beam, because you used a xenon 136 beam, which is a rather stable beam in a sense. So it reminds me of previous experiments of MNT where they used xenon beam on platinum targets, and I think that using xenon beam stabilizes a bit the beam-like product, so it will hinder a bit the transfer from the xenon to the uranium. So have you considered using like maybe a bit heavier beam so that you can have some transfer to add nucleons to the uranium or not?
Okay, so about the beam, yeah, you're right. It's known that MNT, the shell effect will usually play a large part, and well, I think you're right, but no, for this experiment, let's say we have an heavier beam. So I just said that this xenon was scattering and that it was preventing us from reaching the optimal conditions for the use of the separator. If we now have an even heavier beam, it will become even harder because the magnetic rigidity will be much nearer it will come closer to uranium. So best conditions are, as I've shown, best conditions are to have very heavy beam on very heavy target. But doing so, then you just have everybody that end up in the focal plane. So there's some competition for the on the experiment planning, and it's not it becomes harder to make an experiment work with heavier beam.
Okay, thank you.
One last question, if any. Yes, Ferouz?
Hello, Jonathan. Could you come back, please, to the transparency when you showed your results for the cross-section?
Yes.
If I look well, your data are systematically a factor 2 below the predictions. It looks like a systematic effect. Do you have an explanation for that?
Well, I'd say not yet because so I'm pretty sure for the order of magnitude of my values, but as it's some preliminary results and I still have some parameters on which I should fine-tune the computing. So not everything is exactly finished, and I expect my points to move a bit. So it's not obvious yet.
Yeah. Okay, thank you.
Okay, then let's close this session. Thank you once again, Jonathan, for this talk. And the next one will be in a month, and will be by Hugo Jacob, a PhD student at IGC Lab, regarding pairing. Thank you very much all, and till next time.
Thank you.